Thank you, Oleg. Yeah, you're wondering why I am here today. The reason is that this talk is normally a talk of our lab series at the Institute of Computer Graphics, which we outsource to you today. So it's my pleasure really to introduce to you Amanda Prorok. She is a professor of collective intelligence and robotics in the Department of Computer Science and Technology of Cambridge University. I met her during my research visit in summer. And she is interested in multi-agent and multi-robot systems using machine learning. That's why you are involved. She did her PhD at EPFL. That's where I do my research time next summer. And I'm looking very much forward to her talk on using graph neural networks to learn to communicate, cooperate, and coordinate in multi-robot systems. Amanda, it's yours now. Amanda, you need to unmute your microphone. You're still muted?
There we go. I just had to regain control over my mouse. Great. Thank you very much for the introduction. Hi, everybody. It's a pleasure to be invited to speak at the seminar today. So as already kindly introduced, I'm going to be talking a lot about graph neural networks today and how we deploy them as our workforce tool when learning to communicate, cooperate, and coordinate in multi-robot systems. So I'd like to begin with a vision of what we do in my lab at the University of Cambridge. So I really like the saying that the next wave of computing is all about agents that communicate and coordinate. And the reason that I really believe in this vision is because we're currently being driven by a confluence of AI, communications, and mobile computing. And these various technologies are rapidly advancing and coming together to really enable this new phase of computing. So this being said, multi-robot systems is one instantiation of this kind of collective compute. And we actually already see a lot of applications that are, to some extent or another, exploiting the facilities of multi-robot systems. So we can see transport, environmental monitoring, logistics, agriculture, and cooperative carrying of objects for various purposes. And you can think of all of these collaborative robot systems not only as systems that are helping us with spatially distributed tasks, but simply because the tasks, they actually benefit from the cooperation amongst multiple agents. And the benefits clearly are that if we succeed in automating parts of our lives with these systems, we stand to gain a lot of benefits in terms of alleviating the pressures of urbanization and dense living and also environmental change. So this is a bit of the motivation. There we go. What consists of a research program within this domain? And I really like beginning my talks with this overview, this cartoon that classifies the different kinds of problems you might have in collective robotic systems. I like to think of the 3 C's. So we have coordination, cooperation, and collaboration, where coordination, we're really thinking of applications that improve in terms of performance linearly as a function of the number of robots. In cooperation, we have a threshold effect. So below a certain number of robots or cooperating agents, there is no perceivable change in performance, but suddenly you can reap performance change. You can think of traffic or communication coverage as one of those cooperative performance metrics. And then collaboration is when we have an increase in performance, but only as a function of complementary robot types. So you're thinking of systems here that are no longer homogeneous, but heterogeneous, where different kinds of robots or agents come together with different types of skills, either cognitive or physical, and help contribute to the solution of tasks. If you think about these 3 C's in terms of learning, you can think of individual objective functions where you might have any degree of alignment amongst agents in coordination. In cooperation, there is a global reward, and then there's also this underlying notion of the agents sharing the same goal. And in collaboration, you have a shared goal, but there's interdependence between the individual value functions because the robots depend on each other because they are different. Okay? So why is it that solving the 3Cs is so hard, right? And this really frames my research program. So designing practical methods for effective collective multi-agent systems is what we would like to do. Now, it's hard because you can model these systems as fully observable and centralized. But if you do that, you're often going to be encountering hardness of the actual problem. So if you think of many coordinated decision-making problems, such as pathfinding, they are classified as NP hard problems to solve from a centralized perspective. Instead, you could say, well, we can decentralize our systems, render them partially observable to alleviate some of the computational constraints. But decentralizing systems, especially if you are aiming to achieve optimal or near optimal performance, requires that you recover, at least to the best of your abilities, centralized information or centralized state representations. And then because we're partially observable in decentralized systems, we require communication to overcome this. But then the question is, who do you communicate with? What do you communicate, and when do you communicate? And these questions need to be answered in principled ways that hopefully are effective beyond just application targeted single shot solutions. And even if we can solve number one and number two, the problem of transitioning to the real world still persists. So we can design these solutions in simulation, but as we transfer them to real robots, the robots break or unexpected distribution shifts happen, and our solutions need to be able to deal with those. And beyond that, robots can simply fail and be faulty, or they can even be manipulated. And then the question is, how do collective robotic systems deal with that, and how can we guarantee certain mechanisms that provide performance guarantees under all these conditions? So clearly, we can address these problems with either first principles-based solutions or data-driven solutions. And my talk today will really be about some data-driven approaches that we've been developing in my lab since I initiated it a few years back. So the core question we ask ourselves is, can autonomous agents actually learn to coordinate? So clearly the answer is yes, but how do we do this? So we begin by representing agent relationships as graphs. And we then exploit the structure of the underlying data to facilitate the learning problem. So we implicitly are inducing an inductive bias on the data by saying our agents are representing the vertices or nodes of these graphs, and the edges are representing the interaction topologies. And by structuring our data in that way, we're going to have the agents try to learn how to model their interactions. They're going to try to learn what they are supposed to communicate to one another. And they're going to try to learn how to make their local decisions based on the information that they receive from other agents and from the environment. So how do we go about modeling this? So I'm going to begin by showing you the most basic level model that we could consider that captures the interactions between two agents or two robots. And so what we see here is basically we look at how the observation of a robot J affects the action of robot I. And what we're interested in representing here is how this interaction feature, phi of Zj, is processed by agent I in order to affect its final downstream action. And the question we're answering here is, well, how does robot I use this information coming from its interactions to help it make decisions about what it's going to do next? This formalism here, what we're going to do next is we're going to generalize it. We're going to generalize it to any number of n neighbors in the vicinity of robot I. So we're simply saying that we have all these robots making their own observations. They're pre-processing them with some function f of oj. And this is going to produce local features z sub I for all the agents in the neighborhood of robot I. And so the only difference between the formalism I showed you before and this one is that we're now assuming we have some means of aggregating these interaction features z sub I through the function phi. So we have an aggregation function. So now we get to the actual maths of the system, and I'm going to show you how we formally abstract it. So clearly, our robots are the vertices of the system, and they're connected by their interaction topologies. Robot I is then simply modeling these interactions through hidden features H sub I, which is the result of the function phi that processes these incoming features in a permutation invariant matter. And this is important because the order in which the information comes in has no impact. The graph topology here is our interaction topology, as I already mentioned before, and it induces this inductive bias on our learning paradigm, which we have been seeking. So this formulation that I'm showing you here within the function phi captures all the various flavors of graph neural networks. So we have these interaction features, the local ones Z sub I, we have our neighborhoods J of N sub I, and we have an aggregation over this incoming information. But I'm going to give you a very specific example so you can concretely imagine what this actually looks like as we go about implementing our graph neural network. And so what you can see here is an example of a graph convolutional network where the aggregation function is simply given by a sum operation. And our topology is given or represented by an adjacency matrix where we have zeros for no connections and ones for interacting agents. And in the bottom line, you can see how we now can very conveniently write this in matrix form with, on the right-hand side, the nonlinearity and a hop operator aggregating over all the various communication hops we have in our system. So if we only have a one-hop communication network, this capital K is equal to 1, and we're just aggregating over our adjacency matrix. And what's really nice about the right-hand side equation is that you can now explicitly see how we're exposing the learnable parameters W, which right multiply our interaction features Z. And those parameters are the ones that we're going to be learning. So now I'm going to move on, use this framework, and demonstrate the various things we've been doing with graph neural networks in multi-robot systems. So the first thing I'm going to show you is how we've been using graph neural networks to model complex physical interactions between robots. So at this stage, we're not learning the communications, we're just learning how to model the interactions. So a really interesting problem in the area of robot flight is the problem of downwash, right? So you have drones that are supposed to keep or track set points or trajectories in space, yet they cannot do so at high precision in close vicinity or close proximity to other drones due to the aerodynamic impact of quadrotor blade downwash. The problem is here clearly that these aerodynamic disturbances are very hard to estimate in a manner that is real-time capable, that we can actually include into our control loops, because first principles modeling frameworks usually depend on sophisticated numerical simulations that simply just don't compute fast enough that we could use them in a practical sense here. And so clearly we're looking to run inference. We're looking to deploy a neural network that can approximate these downwash forces simply as a function of the relative position between the robots. And of course, inference can then be executed within a couple of milliseconds and integrated in control loops. And that is essentially the aim of the study. We're going to try to develop such a model. And so what do? We model the interaction by saying that there's an external force that we have to estimate. This external force is normally not observed, but we can deduce it by knowing something about the relative positions of the robots. And so we simply say we're going to train this neural network to predict this external force, and we're going to integrate it into our dynamics model, and hence our controller will be able to counteract it. So we're going to learn the parameters of f sub x, and the requirements of this model is that it's going to have to predict not only downwash forces in the up and down direction, but also laterally, right? Which is something that very few people have attempted thus far. We need the model to run very quickly, so super 50 hertz. And we need the model to be small because we're going to fit it onto a Raspberry Pi computer, which is what our customized drones that we own in our lab run on. Okay, so we want to facilitate onboard real-time inference. And we develop a couple of tricks in order to make this possible. So one of the tricks that we deploy is the fact that we can make these models very small because we exploit the symmetries of the downwash. So you can see here in this little movie, we have green and blue drones moving into the downwash zone of the red robot. And the downwash that they're actually undergoing is the same downwash force, just rotationally shifted. So these symmetry effects can significantly alleviate the model training procedure because we can be much more sample efficient. So if you consider collecting a data point within this ring, that data point can be used an infinity of times for the same height under the system if you rotate it around the ring of the red robot. So this is so this kind of symmetry is something that we can very nicely integrate and include into our neural network architecture, not only making it more sample efficient, but also reducing its size significantly. So we do this. We simply induce this idea that in the frame of the leading vehicle, we have equivariance around, or the equivariance of rotations around its axis. And we encode it as a geometric prior into our learning algorithm. And then we train the system to produce a model that, that essentially predicts these patterns in that equivariant constrained way. And so the result of this is that we now have a model that is very compact, that runs very quickly, that has very few parameters, and is able to produce course predictions in the 3 dimensions we were seeking. And you can see in this video, we're now deploying it on board a robot with superposition of with and without disturbance rejection. And the blue robot is the one that's running our model. And you can see how its flight tracking is significantly improved over the robot that is not running any disturbance rejection model. So now you might be asking yourselves, well, this is just a pairwise interaction. How would we scale this if we're flying tens of robots in close proximity? How do we use this interaction topology? Well, we've thought about this, oh yes, but before I get to that, I wanted to show you another example, actually, of how we can actually use the downwash model. So this is an example of docking, where you can of course dock robots at greater distance, but that creates large instabilities amongst drones. And so by using the models that we developed, you're going to shorten the docking mechanism size and facilitate docking at close vicinities to stabilize the contraption of the docking platforms that we've developed. So here you can see running with the model and how it is very nicely able to maintain the height, dock, and also undock again from this contraption. If you don't have the model, you're not able to actually achieve the docking mechanism. And so you can see here both robots in free flight, and the docking mechanism is successful. So this is one use of the pairwise docking, of the pairwise downwash model development that we've come to. So now moving on to this question of, well, how do we scale this model when we're flying multiple robots in swarms or in larger groups? We've been thinking about how would it then be if we would try to increase the scale of the system, basically. And the key question we ask ourselves here is, how do the forces actually aggregate? By what mechanism or by what mathematical construct? So we can think of 2 potential hypotheses for starts. We can either think about linear models, where we have a pairwise aggregation of the forces that we predict between any 2 robot pairs. And this is actually the first variant, or the first hypothesis we have, is actually really practical. Because if we have pairwise aggregation of forces, then all we need to do during training time is train pairwise interaction models. And then at runtime, we simply aggregate the various pairwise model results. Or we're saying that the model is nonlinear, by which we assume that the linear extrapolation would not work. And we're essentially assuming that there is some k-wise relationship between the robots and the drones producing some downwash force that is dependent on the specific formation of the drone's information. So of course, this is entirely possible that we end up with this nonlinear conclusion, but it would be unfortunate because it would mean that the training is significantly exacerbated, because for every given formation, we need to be able to train this model for any given number of robots in flight. So we went about designing a system that could actually evaluate these 2 hypotheses before deciding how we would proceed. And so my PhD student designed a 6 degree of freedom loads down setup, which would allow us to measure 6 degrees of freedom of forces. They were all being isolated and damped through couplers. And this robot was set up on a rig. This is our ground truthing robot measuring the ground truth forces felt. When its rotors were spinning, was set up in such a way that 0 load was felt and measured by the robot. And so all the robot was measuring was effectively the load felt by any robots flying around it in its vicinity. And so we then collected a whole bunch of data with robots flying in formation. So here you see 2 flying in formation, and then later you will see 3 robots flying in formation above the suffering drone. And we then used all of this data to evaluate our 2 hypotheses and see how our models would be able to predict what kind of downwash patterns were produced over the suffering drone, and what models might provide a suitable fit. And so we made a couple of insights. The first one was that the downwash function remains fairly narrow above the suffering drone. The second insight was that it's actually much easier to model the systems at closer proximity, and the errors become larger for positions that deviate in the 2-dimensional plane away from the robots. And the third insight, which is potentially the most interesting one with respect to our hypotheses, is that there were indeed complex nonlinearities that we observed when the downwash actually emerges. And then so in those particular flight patterns where we have the event or the occurrence of merging with downwash, the linear model would clearly not suffice. And so we identified different flight modes in which linear models might be enough, and which nonlinear models, and then the ones in which nonlinear models are required in order to reproduce the forces with high fidelity. So now I want to move on to the other thing I wanted to talk about today, which is going beyond just modeling physical interactions. We want to be able to use the graph neural network structures so that they can tell us or guide us to how we're going to generate communication between robots. And so what I mean by this is not only are we going to be modeling interactions, but we're actually going to synthesize them. And by synthesizing interaction, I simply mean we're going to use these neural networks to create the messaging between the robots, the protocols, actually, the communication protocols. So in other words, we're using the graph neural network as a differentiable communication channel. And we're going to be conditioning it on the conditioning of the actions that the robots execute on the information received, on these encodings received through the graph neural network-based communication topology, communication strategy. So if we string all the elements together and we think about these policies that are being conditioned on information incoming that is processed through the GNN, you can see how the neighborhood observation is the result of our communications function phi, as well as the local processing on each robot's own observation. So basically, summarizing this, we're now actually able to define how outgoing information is encoded, as well as how the incoming information is being processed, and how this whole pipeline affects the action of the receiving robot. And a lot of my students and postdocs in my lab have been contributing to this research thrust, and I encourage you to look at the respective papers for various different aspects of this research. So I'm going to show you a couple of examples of how we do this, and I'm going to begin by motivating the context of why we actually do differentiable comms and why this is a relevant methodology within this context. So if we look at the space of problems in robot groups or multi-agent groups, we can construct this overview where we look at the difficulty of solving the problems in terms of, in the vertical axis, partial observability, and on the x-axis in terms of higher degrees of freedom, so configuration space, complexity. So as we go up the vertical axis, we're looking at more and more partial information, so less information is available at real time. And in the x-axis, we're looking at more complicated, larger, and interdependent agent systems. So we have good solvers when the systems are relatively small but provide partial information. And we have good solvers for when we have centralized information. So everything is available a priori for larger scale systems. So there we're in the offline approximate regime. A TSP solver is an excellent example of a solver that exploits heuristics to solve these kinds of problems. But what we're missing is solutions that can operate at large configuration spaces, within large configuration spaces, and with the constraint of having partial observability, so very little information available to individual agents at any given point in time. These systems are often decentralized, yet they have to be resilient, and we want them to satisfy some global objective. So the question is, how do we achieve all of this? and learning the communication patterns that the robots need to execute. So what strategies they need to use in order to disseminate information is really crucial to making this orange box a green one, crucial to facilitating solutions for this. So I'm going to begin by showing you one example that is really demonstrative of what capabilities GNNs have for very hard coordination problems. So the multi-agent pathfinding problem is a very hard problem in the multi-agent domain. And we were looking at this problem to try to answer the question of whether we can automatically synthesize local communication and decision-making policies to solve this problem. It's interesting because it is an NP hard problem for which we actually have optimized solvers, so optimal solvers. And we would then use those optimal solver solutions to compare our solutions, so the quality of our solutions, to what would ideally be possible basically comparing it to the optimals. So if we reach the optimal levels, we know that there's nothing else that we can do to make our systems better. Yet we want to derive policies that actually run locally on the agents, that don't depend on centralized information, which the optimal solvers do. And we want to try to reach performance that is near optimal, so comparable to the performance of these near optimal solvers. Yet we want to scale more gracefully. So we want to be able to run these on systems of hundreds or thousands of nodes where the optimal solvers clearly break. So we set up a learning architecture where the pipeline consists of an agent that processes incoming information. It pre-processes it through a CNN, then deals with that information within the GNN framework, whereby we're actually emulating the communication by simply computing how information is sent and received amongst the agents. And that information is then either sent to an MLP or directly producing action. And so you can see the exact same formalism I introduced to you before, just representing this pipeline that we're now using for this system in question. And for the multi-agent pathfinding example, we're going to use imitation learning. We're going to use imitation learning to copy an existing optimal solver to try to learn what is the pattern of information that we need to be sending to our neighbors in order to achieve performance similar or equivalent to what the optimal solvers are doing. So what I'm showing you in this movie is essentially a juxtaposition of our expert algorithm, which is simply playing out its solution because it was all computed a priori offline with full information, with our solver that is running everything in real time based on local information only. And the surprising or really impressive thing here is you can see that qualitatively, the solutions perform equally well, with the robots achieving their goals at roughly the same time. Yet in our system, everything is happening locally with only partial information, exploiting this communication infrastructure that is being trained to our system. So what we are really excited about this, because what it essentially means is now we have the method of running local communication strategies for systems which are technically compounded by scale and computational requirements that don't make it possible to reach high quality performance in large numbers. And if you are more interested in it, our papers report how we actually achieve very good performance on systems that generalize to 100 or even 1,000 times in size compared to the systems that we actually trained on. So we have very strong transferability and generalizability properties using our system. So let's look a little deeper into the path planning problem amongst agents. It's a very interesting one in robotics, especially because it is actually hard. So clearly, in the discrete domain, there are two ways you can tackle problems. Coupled planning, which is what optimal solvers use, it provides completeness, which basically means we will know for sure whether a solution provides a solution or not. And it also, complete solutions or coupled planners are also capable of avoiding deadlocks because they model the systems in the joint state and action space, right? So what I'm showing you in this graphic here is an example of what might happen if you decouple the solution. So if you decouple the solution, then the green agent might come into a potential deadlock because it starts moving before the blue agent does, and then the blue agent is never able to reach its goal. So that is one of the reasons you don't want to use decoupled planners in systems where you require completeness, because robots, all of them, need to reach their goals, especially in performance critical applications. Now, what we would like to do is we would like to do deadlock resolution. We would like to provide guarantees for deadlock resolution and completeness, not in the discrete world, but in the continuous world, which is ultimately where our robots perform. And we want this to be possible in very cluttered environments with decentralized, partially observable controllers. So this is a long list of requirements, but that is basically the reality of a lot of the robotic systems we see today in the real world and in warehouses. So I'm going to show you now an example of a system that is running a state-of-the-art controller that would succeed, or is supposed to succeed, in such a task. So here you can see 4 robots that are supposed to navigate through this constriction, narrow passageway, and achieve a formation on the other side of these obstacles. We're using a control Lyapunov and control barrier function-based navigation algorithm that has been carefully tuned and exhaustively tuned through a parameter sweep in order to make sure that we actually find a solution for the system. But obviously, as you can see, the tuned parameters, they're not sufficient to actually allow the robots to be able to navigate through the narrow passageway. And so even with state-of-the-art controllers, it's incredibly hard to find a way to get them to do what we want them to do. So I'm just going to set up the problem, and then I'm going to turn into, and after that I will show you how we went about solving this problem with machine learning-based hybrid solution. So we begin by modeling the agent dynamics with flow vectors F and G that describe how the robots move in space and time. And the goal here is to generate the controls U with a quadratic program that computes a minimum effort control at every time step that we solve it. So our QP has 2 main constraints. So basically the objective is to minimize the control effort, but the constraints are A, the CBF constraint, which is basically going to ensure that the robots do not collide with each other, nor with any obstacles. And the second constraint is our control Lyapunov function that ensures that the agents eventually reach their goal. Okay, so then this is necessary because we want our agents to complete the task. So what's important to note here, there are a lot of details in these equations, but the most important part of it for us here is this function alpha, which is a class K function that depends on 2 parameters. It depends on the 2 parameters zeta and eta, which are very important because they define how strictly we're going to enforce safety in our system. So if we have very loose parameters, the robots are going to be very aggressive, and if we have very strict parameters, they're going to be very conservative in their motion. So that function alpha is an important function that we need to tune a priori before we deploy our systems. That's how it's been done thus far in the literature. So as I mentioned, if we then tune our CBFs with these fixed parameters, if they're conservative, we'll have inefficient trajectories, and if they're aggressive, we might end up in a situation where we're telling our robots to execute controls that are infeasible given their dynamics models. So the acceleration values are simply too high or too low. So trying to circumvent that problem, which is what I showed you occurs in these in certain scenarios, we decided that we would deploy a graph neural network to estimate and tune the parameters of our class K function, alpha, in real time as a function of what the robots are perceiving in their local environment. So simply, the graph neural network takes as input the state of myself, so if I'm a robot, of myself and of my neighboring robots, and of only the obstacles I'm seeing in my vicinity. And it will output time-dependent estimates of what the best possible values for zeta and eta might be. So in the 2 time plots, you can see how those 2 parameters now vary across time as a function of what the robots are seeing and doing. And on the left-hand side, you can see a plot of how the robots execute their trajectories through a cluttered space. So here, clearly, we're seeing a succession of their tasks, and they reach their destinations through a quite tight and densely cluttered environment. So the insight here is that our graph neural network enables individual and heterogeneous time-varying CBF parameters within a decentralized control paradigm without necessitating any global information whatsoever. So you might be asking yourselves, well, if these parameter ranges that your GNN found are so good, why can't we just take the parameter ranges and then deploy a fixed CBF paradigm and fingers crossed it still works? Well, we tried that. We tried using the minimum and the maximum of the ranges that our GNN found. And even in those scenarios, the task actually does not complete. So if we take the minimum over the found range, 2 of the robots don't even start moving, and 1 of the robots is only able to execute half a trajectory. And for the maximum, we have parameters that are too aggressive, and the robots end in deadlock because they cannot execute the demanded controls. So here's first, I'll show you a quick little simulation demo showing you how the online CBF is able to very nicely prioritize and deconflict the motion of the agents as they navigate through these scenarios. And in the fixed CBF version, where we are using optimized parameter sweeps to find the optimal parameters for eta and zeta, we don't have success over these specific environment instantiations. So clearly these are difficult environment instantiations because they're cluttered or they have singular points, but that is exactly the issue that we need to circumvent, and that is why online tuning is so important, contextual online tuning. And then we can do the same thing on our scenario again, which I already showed you, demonstrating how we are now able to successfully prioritize the robots through the narrow gap because we're doing an online computation of the parameters, essentially adjusting how aggressive or conservative the robots are with respect to each other, and achieving this deconfliction in an elegant manner. And then the plots, you could see how the parameters are varying throughout time. So one more thing I wanted to talk about, since I think that cooperative perception is such an important problem in robotics, is how we can also use the graph neural network simply to communicate information amongst one another in order for them to retrieve information about the global state of the system. Now, what's special about this particular task is there are actually a couple of things. But the first one is, so what we want to happen here is the robot is a blind robot. Essentially, it needs to navigate to a target which it does not see at the beginning of a task. So the target is the block in green, and the robot cannot see it because it's occluded through obstacles. But there are visual sensors in a sensor network that are positioned randomly around this environment. And if at least 1 or 2 of them in this environment actually sees the target, this information is going to be processed, aggregated, and disseminated through our graph neural network-based or enabled sensor network. And the information will eventually reach the robot, and the robot can, as a function of that information, compute a shortest path direction, a shortest path trajectory to the target. So it's like a potential field approach where the visual sensor network will be kind of guiding it through this landscape on the shortest possible path to the target. And so as I played the movie, what you can see happening is how dynamic and reconfigurably flexible the system actually is. So you can move things around, you can move the robot around, you can move the target around, and you can even move the sensors around, because everything is essentially calibration and positioning free. So it's completely flexible, and everything that is being computed here is being computed through visual encodings only. So you see now my PhD student picking up one of the sensors, and you see that as soon as the sensor reaches line of sight of the target, the robot's able to navigate to it. And so this is really the beauty of using a structure such as a graph neural network for this information aggregation and dissemination, because it doesn't depend on any positioning or calibration of the systems. It purely knows how to deal with incoming image features, and it knows how to aggregate them to produce coherent representations of the global state of the world, so that the robot knows how to compute over that and navigate down the efficient paths. So a very cool example of how you might use deep learning and GNN-based architectures for cooperative perception. So in the few minutes that remain, I just want to talk about something that is quite new at my lab and I think holds a lot of promise, which is the question of deploying systems or multi-agent systems that are, instead of being homogeneous, might actually be heterogeneous. So what do I mean by that? So if we have robots that are homogeneous, basically, if you have a policy, we have a system where the same observation leads to the same action for all the robots. So if 2 robots are in the same position, see the same thing, those 2 same robots would take the same action, right? Homogeneous systems are incredibly attractive from a computational perspective because they're able to share parameters across neural networks. Everything is permutation equivariant. It's very sample efficient. And you could even consider emulating heterogeneity through specific methods such as explicit indexing and inferring roles. In a heterogeneous system, however, if two robots are placed in the same position, have the same observation, they would take different actions. Okay, so they are deployed with different action strategies for the same observation. So the functions are distinct. And the problem with that is that, well, we don't only have parameter sharing that is disabled now, but we don't have a permutation equivariant system, and we have an observation space explosion, making everything much less sample efficient and very hard to train. So you might be asking yourselves, well, what are the benefits of actually having explicitly heterogeneous systems, given that computationally it is very challenging? Well, there are actually many reasons why we might think of having heterogeneous systems. And here are just a couple of examples of applications where you want the robots to have distinct policies. You could have formation control, where robots are very specialized roles, or pathfinding, where you have one robot that always gives way and the other robot that never gives way, or football, where you have very well-defined, pre-coded or pre-specified behaviors that you want the agents to execute in a scenario that is very strategic, okay? But we've also found that there are other benefits to heterogeneity, and I'm going to show you one. We've found that heterogeneity significantly facilitates zero-shot transfer of policies to the real world. So if we look at this example, you're seeing the execution and simulation on the top, and in the real world on the bottom, of a very simple policy that has been trained to have the robots switch positions in this very simple corridor environment. Now, the robots, they're just sharing information amongst one another about their relative positions, but they don't actually have explicit information about where they need to go. So there's no explicit global information on on our desired endpoint for these robots. So now if we go ahead and we train these homogeneous policies through inferred roles and simulation, we again retrieve optimal performance, so the robots are able to succeed their task. But now we do the same as we did before, and we transfer those policies to the real world. What happens is the robots do not perform anymore. And the reason that they don't perform is because they're not able to use the homogeneous policies to infer the heterogeneity of the situation. Because there's simply noise in the system, there's noise in the control commands, and so on and so forth, which makes it very difficult for the robots to understand where they're at and what they're supposed to do in those situations. So heterogeneity, the insight here really is that heterogeneity allows the robots to distinguish themselves from each other, to essentially memorize parts of their roles so that they're much more robust to newly encountered noise as you put them into new situations, such as real world or even distribution shifts within the same environment, but from one task to another. And we can show that the same thing persists even if we train homogeneous policies with noise and simulation. And we clearly have superior performance when we give the robots the opportunity to learn distinct behaviors, heterogeneous behaviors. And so this idea that we are retrieving resilience to noise in heterogeneous systems is really reminiscent of the resilience you see in nature, where agents diversify and able to complement each other in interesting ways. So this concludes my talk. I've really shown you a lot of things that are going on in my lab. There is a lot more, but let me just begin by summarizing the key points of my presentation today. So just a few take-home messages. I'd like, if there's one thing you remember from my talk, I'd like you to remember that graph neural networks are a very interesting computational paradigm for multi-agent and multi-robot systems. You can use it for differentiable communications, but also to model interactions. And heterogeneity is significantly underexplored, and we've been working very hard in order to elucidate and give more insight to what you can actually do when you have diverse multi-agent systems. What's next? Well, we're thinking a lot about optimal levels of heterogeneity. We're thinking a lot about verifiability and interpretability of the policies that we're generating. And we're also slowly but surely deploying our systems into the wild outside of controlled and fully observable indoor lab settings. There's a lot more really cool work that's happening in my lab that I had little time to talk about. But please, I encourage you to look it up if you're interested. So better graph neural network architectures, or thinking about how to optimize the environments that the robots operate in, or even more core theoretical improvements to the underlying reinforcement learning infrastructure and algorithms for partially observable systems. With that, I'd like to thank the team who contributed to the work that I've shown you today. And finally, I'd like to thank you very much for your attention. And I'm very much looking forward to receiving any questions and an interesting discussion now. Thank you very much.
Thank you very much. So I'm pretty sure that was as inspiring for the students than it was for me, and the floor is open for questions. And maybe, Oleg, you handle the online questions. I can go around and hand the microphone to people here. Okay?
Sure. Let's start from the audience, maybe. Any questions from the audience?
No? Then, yeah.
Hello, everyone. My name is Michael Ogu. So for me, the key takeaway for me in this presentation is the fact that the system uses a decentralized architecture. And that's from a security perspective. I think that is good because it doesn't have a single point of failure. Now, but we know that cybersecurity is one of the most pressing problems today in technology. So I imagine a situation where we have such a system being deployed in the real world, and then you have attackers attacking the system. So the system experiences a cyber attack. So how do you ensure that the system is not compromised in the case of cyber attacks?
Yeah, it's a great question. I think resilience to non-cooperative adversarial agents is a very difficult problem. We have actually worked on this. I have a couple of papers on it, which I do encourage you to have a look at. We've studied it explicitly within the context of flocking, so multi-agent flocking, where you have certain robots trying to achieve a formation and follow a direction of motion, direction of travel, where they're being corrupted by one robot that wants to manipulate the team to move in a different, distinct direction. And there are mechanisms that can deal with this, but they're very difficult to develop. And one of the key requirements for resilience against non-cooperative or even adversarial robots is that you have some side information that you can trust. If you don't have some side information that you can trust, it's very difficult to filter out manipulative information. So overall, I think security and privacy are incredibly important domains, and it's still an area where I feel a lot more can be done to make our systems more robust and resilient.
All right, thank you.
Anybody?
I have a question. You talked about heterogeneous versus homogeneous. Do you see a difference between a heterogeneous agents and like an agent which is in principle, when you have agents which are in principle the same, but you have some kind of background data like behavior defining variables or something like this, because if they are also input to your network, that would be kind of still the same as if they were part of an observation. So they would still be...
That's perfect. Excellent question. Very, very well identified. So the key point when we say we have a heterogeneous system, we're assuming that there's something that is unobservable about the heterogeneous actors in the system. If it's observable, then it ends up being a homogeneous system again, because you can simply condition on it, and it becomes what we call actually an index. And then you can model everything with a homogeneous paradigm. Yeah.
Does that answer your
Great
question? Okay, any more questions here?
Yes, I have a question. So at the start, for the downwash training, you mentioned that you measured the pressure and trained the model on
yes.
that. Did you also try to use, for example, smooth particle hydrodynamics for simulating the measured values instead of measuring them?
So simulation frameworks?
Even an option. Yeah, simulation frameworks for training the model.
We didn't actually try to use simulation frameworks in order to simulate the forces in addition, because we had the ground truth forces. So for us, it was not so expensive to gather the ground truth data, and there's nothing better than the actual ground truth data. The problem with simulation frameworks, if you're trying to use that in order to produce labels for ground truth data, is that you have to be incredibly confident that you're calibrating every single element of your simulation as precisely as you can to capture the real physical system as it occurs in the real world. So you'd have to know the weight, the size, the materials, everything of your system, so that you're getting exactly the right dynamics, so that the labels generated are exactly right. And if they're off, you'll essentially not be estimating the right labels, because the labels were generated wrongly.
Yeah, and for example, when the height changes, the air density would also change, and that would change the pressure. Did you also accommodate for that? So is the label aware of, for example, the density of the air?
Not sure I understand the question. So when we collect the ground truth data, we're measuring the felt force, the felt external force, which encapsulates everything in the given environment. So potentially, maybe what you're alluding to is, if we were in an open space, that felt force would be different than if we're in a closed space. So indeed, yes, but in that sense, the felt force would be specific to the environment in which we collected the ground truth data.
Yes, that's what I meant, thanks.
Maybe let's take one question from the chat as well. So Amanda, thank you very much for your wonderful presentation. And I wanted to cite Timo from the chat, who is asking to maybe comment on how your research relates to automated traffic control.
So in automated traffic control, you can think of cars that are potentially autonomous or semi-autonomous or just assisted, that could hopefully one day exploit communication amongst each other to infer information about what is beyond their own line of sight. And then the question becomes, well, what kind of information do you disseminate through these car systems, and how would the cars then use this information to do better trajectory planning? A very simple example is, you can have cars around a corner, and those two cars respectively don't actually see each other, and they don't see their traffic scenarios around the corner, but they can see something about what local traffic is doing in their vicinities. And for example, if this car sees, oh, there's a pedestrian crossing here in front of me, I'm obviously going to stop. But that information is very important or crucial for the cars around the corner, because they should already slow down as they come around the corner, right? So there is trajectory planning optimizations you can do as a function of what other cars can observe in their local fields of view that you cannot. And a lot has to be gained from generating and disseminating pieces of this global state information through such mechanisms as I've described to you today.
Thank you.
Any more questions, either here in the room or online? Amanda, for the downwash experiments, we did also some downwash experiments here. Do you consider speed? So
yes.
So speed is one part.
That is a very good question. Very good question. So actually, the most significant thing that happens as we increase speed is that our symmetry assumption, which we're making, that we have a rotation equivariance around the axis of the leading vehicle, it starts to break down. Because as you have speed, obviously the quadrotors, they're non-holonomic platforms, so they have to tilt. So as you have speed, you have this kind of thing happening, right? The robots, the quadrotors fly in this kind of configuration in space. And then you no longer have symmetry, because the rotors here are pushing harder than the rotors here, and then the forces felt are not rotationally equivariant anymore. So we've definitely considered speed, but that is where we start having to relax our equivariant neural network architecture, and that complicates the model a little bit. But we have some really exciting work coming up very soon that that hopefully addresses some of those issues. But it's a very good question and well identified.
I guess you also notice when you are moving with higher speed, downwash is very little. So downwash reduces a lot when you bypass a hovering drone with a higher speed. So that's what we actually observed. Did you also?
It depends where you're flying. If you're flying in the downwash at higher speeds, the downwash is strong.
No, it's little.
But it really depends on your exact relative position with respect to the other, with the leading robot.
So we did similar experiments with a hovering drone and one drone flying below, and depending on speed, how quick you pass the hovering drone.
You mean the speed of the flying drone, the suffering drone, not the hovering drone?
Exactly, yeah.
Yeah, the other way around. Yes, it decreases because because there's a time delay effect and you're essentially spending less time in the downwash. So the accumulation of downwash force is lesser and hence the force felt doesn't accumulate as long and there's a smaller impact. Yeah, that is true. Mm-hmm.
Okay, so any more questions? Yeah.
Hello, Amanda. Thank you for your presentation. I just want to ask a question about the control barrier functions. As far as I know, in swarm control, you may do some upper level controller that gives some speed or the waypoints to low level controller that controls your agents. Let's say your robot, your drones, whatever you use, your system. Also, you may combine them. You can directly connect your swarm controller with the dynamics controller. So there will be one controller. So my question is how you use your control barrier functions in your swarm system.
So the control barrier functions directly output the controls that are executed on the actual platform. So we don't actually have high level and low level controllers.
Okay. Yeah.
But thank you for the question.
Okay, any more question? Online? So if that is not the case, then Amanda, thank you very much again.
Thank you.
Thank you for this very inspiring and interesting talk. And thank you for
Thank you very much for the invitation.
Bye-bye.
Wish you all a pleasant afternoon.
Bye-bye. Thank you for coming.